Okay, well, thank you very much to the organizers for inviting me. It's been a really great time this week. And this morning I'm going to talk about some joint work I've done with Toby Cubitt, my supervisor at UCL, and Tamara Kola at the ICMAT in Madrid. Okay, so I have these two themes in my title that maybe aren't as familiar to everyone in the audience and haven't been mentioned previously in talks this week. So the first being that of holography. So this idea that information that's in the bulk of a space can be encoded at its boundary. So sort of from the word hologram, the ones you get in the little glass cubes. And in particular, the realization of holography in high energy physics and AWS-CFT. And the second being position-based cryptography, which is this cryptographic protocol where you use the prover's position in space-time as its certification. So how you would give your money over to a man who is in a bank behind a counter at like 2 p.m., but maybe not if that same man was like stood on the streets of Coogee at like 2 a.m. And yeah, so I'm going to talk more about these two concepts throughout the talk, but if anyone has any questions about it, please interrupt and I'll be happy to go slow or clarify. And especially towards the end of the talk when I'm talking more about some ongoing and unfinished work, welcome all suggestions and comments, etc. Okay, so these two themes have been linked, and there's some work done by some people at Stanford talking about the link between them. But my research sort of goes via these holographic error correcting codes that were first introduced in 2015 by John Freskel, Fernando Paskalski, Daniel Harlow, and Benny Yoshida. Okay. So in the first half of this talk, or the main part of the talk, I'm going to talk about how we construct these holographic error correcting codes in our construction and are able to prove like nice things about them to do with holography and AWS-CFT. And then at the end, I want to talk about, like I said, some ongoing work of how we can use these codes to investigate these cryptographic protocols. So if you're interested in high energy physics or cryptography, hopefully this talk will be interesting and up your street. But if the things in pink don't initially motivate you, then please bear with me, and hopefully the applications of the techniques and how these quantum information applications are used together in this project will still be interesting and enjoyable to people. Okay, so getting started as promised with some basic AWS-CFT. So this is a realization of this holographic principle. Like I said, the idea that information in the bulk of a space can be encoded at its boundary. And in particular, this is a correspondence between two theories. The one in the bulk is a theory of quantum gravity. And this lives in what we call an asymptotically asymptoticity space-time. So basically, this just means that my spatial degrees of freedom have some negative curvature. And I'm going to draw it sort of like the soup can, where I've got the spatial degrees of freedom on the circle, and then I've got time going up. But as this is gravity, we're kind of thinking in like space-time here rather than distinctly space and time. And this theory is dual to the conformal field theory on this boundary of the space. So if I unwrap my soup can and spread it out, then I've sort of got this flat rectangle. And this is the space that my conformal field theory is living. And you can just think of this as some field theory which has got some symmetries. And the whole idea of like correspondences and dualities is they can be interesting to study, because if I've got some measurement and calculation that I want to do in one theory, then I can potentially do that easier by first mapping to its dual, doing it in that space using some techniques from that theory, and then finding out the answer. So in particular, AWS-CFT has been used to study strongly interacting CFTs, because if I've got a strongly interacting theory, that's hard to model. I can't use perturbation theory. But if I can first map that to some weakly interacting classical, like semi-classical gravity in the bulk, something we have more of a handle on, then I can make statements, make predictions that I can then test in my CFT. And then I guess the real excitement back in the day, or still to this day maybe, was that we could use this correspondence in reverse. So if I then think about a theory of quantum gravity, which obviously would be cool, if that is then dual to just a CFT, that's just quantum information. Like I should be able to understand that using the tools that we already have. Okay, so that's super nice. But the issue is we don't really have a complete mathematical description of this correspondence. So we don't have a rigorous map between these two spaces, and the high energy people do what they do, but without each step being like mathematically rigorously written out. Okay, and yeah, just to say, for the rest of this talk, I'm going to sort of be drawing these circles, where these circles are space-like slices in my supercam, where I still have a 2+1 dimensional bulk and a 1+1 dimensional boundary. And you can think about this circle being any space-like slice in my supercam. Okay, so we don't have a mathematical description of this correspondence. So if we want to investigate what's going on or have something that we can explicitly solve, people do these things by creating toy models, things that look like ADS-CFT on some levels, and hopefully can give us insight into what's going on and get closer to this, what would be great mathematical description. Okay, so if I want a toy model, then I'm obviously not going to go straight for full ADS-CFT. So maybe there are some like particular features of the correspondence that if I have in my model will still be interesting and allow me to tease out some things about what I'd expect in different scenarios. So I'm going to go through 3 key features of ADS-CFT that I might want to have in a successful toy model. And the first of which is this error correcting property that was first pointed out quite a while ago. And basically ADS-CFT behaves as an erasure code. So in this way, if you're not happy thinking about bulk and boundary, we can go back to thinking about physical and logical like Hilbert spaces. So my bulk is my logical Hilbert space, and this Hilbert space is encoded with redundancy onto the boundary into my physical Hilbert space. And you can see this by if I have some, can I point? Yeah. So if I have some local bulk operator here, then I can recover this on different overlapping regions of the boundary. So I could erase everything but this red region, and I could still recover X on OX of A, but I could equivalently erase everything but the blue region and recover this on OX of B. So I'm protected from erasure of some of my physical boundary qubits. Okay. So the second thing that might be nice to have in my model to reflect ADS-CFT is if I take some sum of k local terms in the bulk and build that up into a logical Hamiltonian, if I then use this mapping, I expect to have a k-primed, maybe local physical Hamiltonian. And having this sort of locality on both the bulk and boundary is important if I want to study things like energy scales, dynamics, or just having like a mapping between models aside from just like states and observables. Okay, and the final thing that we're going to think about is the entanglement of ADS-CFT. So like I said, the bulk theory is this theory of quantum gravity, and therefore like geometry is exciting for people who like to think about quantum gravity. And the geometry in the bulk of the space is encoded into the entanglement of my conformal field theory on the boundary. And this can be understood thinking about the Ryo-Tevnaki entropy formula. So if I take some code word on my physical qubits on the boundary, and then I trace out part of the boundary, so I then look at the support of that code word just on some subregion A, then the entropy of that restricted code word should be proportional to this cut through the bulk. So in that way, as I like move and the cut is anchored on the boundary subregion A. So as I change which part of the boundary I'm looking at, I'll be looking at different cuts through the bulk. And as the geometry of my bulk changes, these cuts will change, and that will be reflected in the entanglement of my CFT. So these are 3 things that hopefully are like basically how I would understand ADS-CFT. I'm not quite sure about all of the bits. These are 3 concrete things that I can write down and think about. And they're the sort of things that I want to take through to see, like, can I get this in some like explicitly solvable toy model? Okay, so as alluded to the title, this toy model we're going to build from holographic tensor networks. So tensor networks have been talked about earlier this week, but just a quick recap. I'm going to draw my tensors like a little blob with some legs coming out, and each of these legs is going to correspond to some local Hilbert space. So you could think of them as qubits or qudits. And my tensor is just some like multidimensional array that describes how I interact with these indices. So if I think about a tensor with no contracted indices, then this is going to describe a state. And I sort of think of these as two equivalent things. So if I want to define a tensor, I can equivalently just define the state that tensor describes when I've not contracted any of its legs. But the nice thing about this graphical description of a tensor is without really changing anything, I can then, instead of thinking about a state, I could think about some operation where I've got like a set of input legs and a set of output legs, and my tensor is some operation that's taking me from one Hilbert space to another. And I can sort of move these legs around arbitrarily on my little drawings and get some intuition of what's going on. Yeah, and then we can also take multiple tensors and contract them together, building up these networks where contraction of a leg corresponds to summing over that index. So a basic example is matrix multiplication, where I take two matrices, so two-legged tensors, and I contract the one in the middle, summing over that gives me like matrix multiplication. So hopefully all of that is clear. So when you think about building up a holographic tensor network, we go back to this like a space-like slice of ADS. So this circle is my boundary, and in the middle, I've got this ADS space. And here, because I want to work in some sort of finite discrete model, I've tessellated this hyperbolic space with this tessellation. And here you can sort of get an intuition of this negative curvature. So as I increase my radius from the boundary, the circumference of my circle is growing exponentially, as opposed to just with a power law. Okay, so when I'm building up my tensor network, I decide some holographic geometry. I then place a tensor into each cell of my tessellation of the space. And here, each of my little tensors are these six-legged tensors, where I've got the 5 legs and then a blue leg. I contract the tensors with the tensors in neighboring cells of my tessellation. So these are these black contracted legs. And because I've got here a tessellation with 5 sides, that leaves me with one additional dangling leg, which I've colored in blue. And we're going to associate those with our bulk degrees of freedom or our logical qubits. And then at some finite radius, I'm going to stop adding tensors to my tessellation and instead just leave all of my the legs that would have connected to like the subsequent layer and just leave them dangling and associate these as my boundary degrees of freedom or my physical qubits. Okay, and then like I said, we can then think about this tensor network as describing a map from my bulk degrees of freedom to my boundary ones. And I can think about sort of pushing operators through this map. So if I take some bulk operator and I contract it with my bulk degrees of freedom, then I can look at that as just a boundary operator on my boundary degrees of freedom. And yeah, so this was first introduced in 2015. And when I'm making these models, I've sort of got a few choices. Like I've got choices of how I tessellate my hyperbolic space. And then what is the tensor that I choose to put in each cell? And those choices are going to reflect what we can prove about these networks and their properties. Okay, does anyone have any questions about any of that?
Can you just first again on like why the bulk operator construction works that way again? That it's like in the positive wedge.
Some intuition, like from. Okay, so from like the ADS-CFT side, I don't have loads of intuition, but I'm going to go through like from the tensor network model how we can see how that's the sort of erasure that we can recover from in a tensor network model. But yeah. Okay, so like I said, the choice of tensor is going to be really important here. And we want all of the information from our bulk or our logical space to be preserved in my physical or boundary space. So I'm going to want to have some sort of isometric map to ensure that none of this information is lost. And if I choose just any old tensor, then that's not going to happen. So it's really important that I choose isometric tensors to build up my network with. And this introduced this special class of tensors called perfect tensors, which are basically these tensors that describe isometries between two spaces. And like I said, you can think about these as describing as describing special types of states. And these states are the absolutely maximally entangled states. And these basically, if you've not come across them before, is like, if I think about these tensors and I think about taking the, like any bipartition of my legs. So I could do this one I've done in gray over here, or I could do like any other, and it doesn't need to be like geometrically. So I could take these two and this one as like 3, and then those are the other 3. I'm always going to be maximally entangled across that cut. And these are obviously special kind of states, and they correspond to perfect tensors. And the nice thing about these perfect tensors is they do exactly what we wanted. They describe encoding isometries. So if I take these tensors with some amount of input legs and some amount of output legs, then the map that that tensor describes is an isometry, as long as the number of input legs is less than or equal to the number of output legs. And when the number of input legs and output legs are equal, then it's going to be a unitary. Okay. And another nice thing about these perfect tensors is they correspond to good error correcting codes. So if I think about the 6-leg perfect tensor, that describes the 5-qubit code that encodes 1 logical qubit and 5 physical qubits and has distance 3. And distance 3 means we can recover all information after erasure of any 2 output indices. Okay, and yeah, like I said, they have good error correcting properties, and we can quantify this by saying they saturate the quantum singleton bound. So they're the best we can hope for in terms of like distance and number of legs. Okay, but another option that people have used to construct these tensor networks from are random tensors. So these are tensors where the state is a random state, and you can think about these as like if I take a reference state and then I apply a random unitary to that state. And these have been shown to be approximately perfect tensors if the dimension of the indices is large. And you can sort of think about that because if I take a really large dimension state, then with high probability, that's going to be maximally entangled. And yeah, so the previous work on these tensor network models have used either perfect tensors or random tensors. And the nice thing is, because we know that perfect tensors are approximately with high probability perfect, all of these like isometric properties carry through with the random tensors, with the additional bonus that in the random case, they have this entanglement structure that we wanted. So they have this idea where I can take the entropy of some reduced code word, and that corresponds exactly to this cut through the surface. I'm not going to super go into how that works, but if you want to talk to me about that later. Okay, so if I think about these six-leg perfect tensors or the 5-qubit code, you can see how we're going to get exactly those error correcting properties that I spoke about before. So say I have some bulk operator here acting on this leg, then I can think of this tensor here, the central tensor, as having 1 input leg and 5 output legs. But because I've got distance 3, I can say, okay, I'm going to just erase these 2 and just track these 3 through the network. And then again, I've reached 3 new tensors, which are still describing the 531 code, 513. So again, I don't need to use all of the output legs, and I can choose 3. And if I preferentially keep choosing 3 to sort of like push towards the boundary in some like direction, then at the end, I end up being able to recover the information of this bulk index by just looking at this section of the boundary, which is sort of what I described before in terms of what we wanted in ADS-CFT. So I could erase all of these other boundary qubits, and I've not lost any information. And you can see how I could do that in like multiple different directions, especially with the central tensor. So I could like rotate around, and there's going to be lots of different regions where I can perfectly recover that information, given erasure of some other section of the boundary. Okay, so that's sort of why I like these isometric codes tensors are important for the error correction properties. However, when we look at if I've then got this sum of k local terms in the bulk and I want to push that onto the boundary, let's see what that looks like. So like, say I have this term that's close to the boundary, then I'm going to be able to recover that on, this is the smallest set of boundary indices that I can recover on. And I could have pushed it in another direction and recovered it on like a much bigger one, but this is like sort of the smallest region. So this is, yeah. But then if I go deeper into the bulk, I again do the same procedure, and I end up like requiring much more of the boundary. So this is one of those codes where not every bulk index has the same level of protection against erasure. Ones near the boundary are much more vulnerable, because I could just delete a few boundary qubits here, and then I'm going to need like a lot of the boundary in order to recover it. And another thing to note here is that if I've started with this local bulk Hamiltonian, but like I've then ended up with this term on the boundary. And this isn't necessarily like a tensor product over all of those, like a nice local tensor product over all of those boundary indices. This in general is going to be some global operation on those three. So it's going to be things that are all of this local, which isn't really what we wanted. We wanted a local bulk Hamiltonian to correspond to a local boundary Hamiltonian. Yeah, so if I use a tensor network code alone, either with perfect or random tensors, then this is going to give me a good toy model of states and observables, but not for Hamiltonians or dynamics, because my Hamiltonian on the boundary is going to be this like thing that acts on like globally on a large region, and all my causality is going to be things whipping around the boundary at like unphysical rates. Okay, so this is where we need, oh, sorry, I hope you can see that. This is where we need to use some more techniques. So we've got our error correcting code, but we've got this problem that we've got this global boundary Hamiltonian, whereas what we really wanted was a local one. So this is where we're going to use techniques from Hamiltonian simulation. And maybe people, yeah, this is just a quick slide of introducing what I mean by Hamiltonian simulation. So I'm not talking about like digital simulation here, where I'm going to trotterize my Hamiltonian into some circuit. I'm talking about analog Hamiltonian simulation, where I've got some Hamiltonian with interesting physics, H primed, and I've got some simulated Hamiltonian H. And I'm really going to try and engineer the physics of H primed into the Hamiltonian of H, so that they behave with the same physics. So if you can think about, if I wanted to model an airplane, then a digital simulation would be like, I do some computer model of the airplane. And this sort of analog simulation would be, I build the aerofoil and I put it in a wind tunnel. And there's still something to be gained there, because I've got like artificial control of my aerofoil. I can do like different things. That's easier than just studying the airplane like flying through the air. But it's a bit different to like if I was doing an actual like digital simulation. Okay, so I've got this Hamiltonian H prime, the one I'm interested in the physics of. I've got this simulator Hamiltonian H, which is like easier to make in some way. And I want to know that the physics I end up with over here in H is going to be close to that of H primed. So if it's perfect, then if I take this, I've defined this simulation map here. If it's perfect, then these two Hamiltonians are going to be in operator norm completely equal. So all of the eigenvalues are going to be the same. All of the physics is going to come out the same when I do any sort of like measurement or look at the partition function or anything like that. But in general, that's not going to give me too much. So maybe I want to think about a simulation into some invariant subspace, i.e. the low energy subspace of my Hamiltonian. So maybe I take this simulated Hamiltonian and I just look at its low energy states. If that could still be close to the physics of my target Hamiltonian, then that's still interesting. And then one step further, what if I think about allowing some sort of approximation here? So I'm again looking at the low energy subspace of my artificial Hamiltonian that I've got control over. And now it's not going to be exactly the physics of my target Hamiltonian, but it's going to have some controllable error that I can track through my simulations and check doesn't get too big, or twist certain knobs to make it smaller if I need to. Okay, so we want to try and use these techniques from Hamiltonian simulation and use them to help us build a better toy model here and get these local Hamiltonians on the boundary. So in order to do that, I first need to think about this whole thing as a simulation. So I've already got my quantum error correcting code that's described by my tensor network. And this can easily fit into this framework because this tensor network encoding is a perfect simulation into the subspace. So in general, quantum error correction is perfect simulation because I'm getting all of my measurement outcomes if they're obviously like in theory, with probability 1. So here I've got my H boundary that's equal to applying the encoding asymmetry onto H bulk. And here it's into the low energy subspace where I've added this term, which has got support on the complement of the code space, and I'm adding some high energy penalty to this. So you can think about this is sort of adding an energy penalty to every stabilizer that I validate, that I violated. Okay, so in this case, if I then look at my boundary Hamiltonian restricted to this low energy subspace where I've not violated any stabilizers, then this is going to be like exactly my my bulk. Okay, so we've got our first step, which is a perfect simulation. But in order to go from this global Hamiltonian and make it local, I'm going to have to start using techniques that allow some approximation. So these approximate simulation techniques are powerful, and they morph the Hamiltonian interaction graph while retaining the physics of the properties with some error that I can track. And we use some different techniques for different cases. Like there are other options, but a nice example of this is perturbation gadgets. And these actually come from Hamiltonian complexity literature. So these are some like hopefully intuitive examples of how these gadgets work. So I could take some k-local interaction, and I can simulate it by adding in some ancilla and then having two interactions like this. I can also remove crossings. So say I've got a graph that looks like this, I can add an ancilla in the middle, and I can simulate it with something that looks like this. And I can also reduce the degree of my vertices by taking this one that's got 2 down here, and now it's only got 1 interaction touching it. So in general, these perturbation gadgets are allowing me to change the shape of my interaction graph while retaining the physics with the trade-off of adding in some extra qubits and obviously changing what these interactions are. Okay, but this is nice because we've got our tensor network encoding, which is the perfect simulation. And it's going to take me from my local Hamiltonian on bulk qubits and spit out some non-local Hamiltonian on boundary qubits. But I can then use these approximate simulation techniques to take this highly non-local Hamiltonian and spit out some local Hamiltonian on this new set of boundary qubits where I've now additionally got some like extra ancillas in order to do this localization. But we can compose these together and sort of track the error through it. And we end up with some nice approximate holographic error correcting code that takes me from my local Hamiltonian on bulk qubits to some local Hamiltonian on a new set of boundary qubits. The error correcting properties that I discussed before are going to now be preserved approximately. But I've gained that my boundary Hamiltonian is now localized. So I now have like a truly local Hamiltonian on the boundary. Okay. Yeah.
It's going to be that this boundary Hamiltonian simulates the bulk one only on this subspace, or?
Yeah, so there's going to be some like higher energy levels in this new local Hamiltonian that is just sort of junk. And we're going to have to look at the effective low energy theory of the boundary Hamiltonian in order to get the bulk physics back.
So you're never going to be sort of lucky and prime that even though this local Hamiltonian bulk perhaps doing a non-local one on the boundary, that there is sort of an equivalent local one that just acts on the desired subspace. You need to use these gadgets and add the qubits and everything.
So in terms of like the tensor network models, if you always end up with something that acts like globally on your boundary, but obviously like that's not necessarily the only way you could do this mapping. So I think people wouldn't say that this is like a necessary ingredient, but like when we've already got these tensor network encodings, this is sort of like something we then have to do to add it in, because in real ADS CFT, they just map it and then they get some local CFT, but no one's really sure how they're doing that. Or then, yeah. Yeah.
Say something about what like what is the goal doing the goal outside and what language memorize?
why can't we trotterize? Okay, so I guess the general goal is to be able to have this dictionary between the two spaces. So hopefully at the end we get time to talk about some protocols that you might want to think about in ADA-CFT. And if I've got some like two local theories, then I can start thinking about if I put that Hamiltonian in the bulk, what happens on the boundary, and I can then look at what that looks like, look at how the entanglement works, and find out things about quantum information. Why can't we trotterize is, I guess, because like we don't actually want to like run this on a quantum computer. Like, well, I guess you could, but like you just be running like one time step. The idea is we really want something that's going to like dynamically be moving like the same way the bulk is. Well, we want sort of both, I guess. Like in the real case, you have the, like it's a bidirectional map. It depends like where you're starting with and where you think. Like if I'm starting with something where I want to learn about quantum gravity, then I'm going to start with something that looks like quantum gravity and then map out maybe. It's just like depending on how you want to use it. Sorry, I don't think I answered that very well.
Can you explain again why you introduced these additional terms for the boundary Hamiltonian?
Why we have these extra qubits? So they're just okay, so it's not really like I'm adding extra terms. It's really like I'm constructing a whole new Hamiltonian. And this Hamiltonian has the nice property that it's local, and the physics of that is close to the original one.
And but why is like I guess I don't fully understand the logic. Like, wasn't the goal that the holographic mapping gives you the local boundary Hamiltonian exactly right?
Yeah, that would be the goal, but the tensor network doesn't give you this local Hamiltonian. It gives you a boundary one, a global one.
Okay.
So like it would be nice if you could come up with some tensor network that takes you straight from this to this, but we don't know how to do that. Yeah.
So can you just the exact holographic mapping, like a wavelength go from a boundary to the
Sorry, use what?
well, it's like there's an exact unitary multi-scale test game.
Mm-hmm.
That was mapping from a boundary to the bulk. Although you'll have longer range.
You have longer range couplings.
Yeah.
Oh, okay. Okay, so I guess the first thing, okay, I'm not super familiar with that, but I think maybe some points to make is having, even if it's like a k-local, we sort of want it to be geometrically k-local, like around the boundary. If I again have like, even if it's still too local, but it's between like two things on opposite sides of the boundary, then all of my causality and that Hamiltonian isn't gonna look like a local Hamiltonian in the sense that I can look at light cones of operators, for example, because I'll be messed up. I had another point, but I can't remember it. But maybe we could talk later because I'm not actually super familiar with the thing that you're talking about. Yeah, okay. Okay, so this is our general scheme, I guess. But yeah, just to get some intuition of sort of how this perturbation gadget, like breaking down of the boundary Hamiltonian works, I've just got like a toy example. So I've got, say, some interaction graph here where I've got some 2 local things that are red and I've got some 6 local things that are blue. And I want to end up with something which is like say three local. So I need to start applying rounds of simulation. So the first round is, say I use the subdivision gadget to subdivide those blue ones into, instead of 6 local, I've now got 4 local. Maybe I subdivide again. Maybe I use the forking gadget to reduce the degree of some vertex so that it doesn't get out of control. Maybe I subdivide again, and I end up with some like mess of a Hamiltonian. But this Hamiltonian will have the same physics as the first one. And if I did this properly, I could get some nice interaction graph. I could keep going, go to 2 local, make it geometrically local, et cetera, et cetera. But as pretty and as fun as I find drawing these diagrams, it's not really the most useful way to build up these simulations. And the real thing that we're interested in is this cost of localization. So as you can see here, I started off with 9 qubits and I end up with 9 plus 7 gadget qubits. So I've increased my number of qubits sort of by a factor of 2. And this is the sort of thing that I want to keep track of. I don't want to increase my number of qubits loads and loads. I don't want to do like an unfeasibly large rounds of simulation, because this is like the price I'm paying for gaining this local nice graph structure. So I want to keep track on how many extra ancillas I'm adding, and also sort of a bound on what's the highest interaction strength these new interactions are, because we're adding in these like higher penalty terms, and these can keep growing and growing. So if I do like an exponential number of rounds of simulation, I'm going to end up with a really large interaction strengths, and maybe that's not super useful for my model. And the size of this cost is going to depend on the starting graph. So if I start already really close to a two local interaction graph, and I need to do like 1 round, that's obviously not going to add too much in. But if I start with some complete graph, then that's obviously going to be a lot worse. And I really want to have some sort of reasonable scaling for these holographic codes. So I start with my non-local operators on these qubits. I do my techniques, and I'm adding in some ancillas. But like I said, I don't want to add in like exponentially many ancillas in N, or like even poly, because then if I think about rescaling this boundary Hamiltonian, it's sort of increasing the radius where this boundary Hamiltonian sits if I standardize like how big my tessellation is. So I only really want to add a few ancillas so that it's still sort of sitting close to the boundary, and it's not like blown far away from the bulk and not really being holographic anymore. So with our analysis, we end up getting order polylog n ancillas. But in order to do this, we need to be really careful about what tensors we choose and how we choose to connect up our network. So for example, if I just apply these simulation techniques to Haar random networks, I don't achieve this small number of ancillas. And I get this big blow up, which we don't think would be interesting to incorporate in our model. Okay. So we're going to want to try and control this localization cost. And there's 2 ways that we're going to do that. The first is having some algebraic constraints on the geometry. Like I said, the cost is going to depend on my initial Hamiltonian interaction graph. And I want to try and get a grip of what that looks like. When I take these bulk ones, I use my tensor-network, I end up with this big mass of things. Like, what does that graph look like? And in order to get a grip on that, we use the Coxeter group structure to ensure we choose a network with good properties for our geometry. So if you've not seen Coxeter groups before, this is they can be defined as this reflection group. And this is nice because then we can use this group structure to analyze the tessellation without sort of like drawing it out and counting things, which is easy in 2D, but if I want to go to 3D, it sort of just becomes a mess. So we build up our models by using a tessellation of the space with Coxeter polytopes. And these are polytopes where all the dihedral angles are integer submultiples of pi. But basically, if I start with a Coxeter group, it sort of defines some tessellation of space. And this can be nicely depicted by a Coxeter diagram. So if I'm into a 2D bulk, I can sort of like draw out my tessellation and I can count things like I did before. Like if I've got something here, it goes here. If I have something here, it goes here. Like I can sort of count it out. But this corresponds to this nice simple Coxeter diagram that I can use to sort of do that counting for me. Because then when I go to 3D, I couldn't draw this, but like we end up with these like more complicated Coxeter group diagrams. And then we can use these groups to prove things about sort of like the largest weight of the largest like k local weight of my boundary Hamiltonian, how many of them there are, and on which boundary qubits they act. And Coxeter groups are quite general, so it's particularly here we're looking at hyperbolic Coxeter groups, where if I do the tessellation, the number of cells in a ball of radius is going to increase as tau to the r. And in our work, we use these Coxeter groups to first prove that we get these error correcting properties for particular tessellations. And secondly, like I said, to track this boundary Hamiltonian, like its weight, its number of terms. And that's the starting thing that we need to then figure out how many extra ancillas we need to add when we localize. Okay, So that's one thing that we work through, and all of the math is sort of in the papers. I'm not going into too much of it here. But the other thing is a tensor choice. So like I said, we've previously talked about these two types of tensors. We've got the perfect tensors, which are this special class corresponding to these absolutely maximally entangled states. And then we have random tensors, which have these better entanglement properties, and in the high dimensional bond limit correspond to good codes, and we all have the good error correcting properties there. But the important thing to note here is if we choose stabilizer tensors, these are really nice because they're going to preserve the Pauli rank of my operators. So if I don't have stabilizer tensors, then the Pauli rank is going to kind of blow up. And again, that's just going to add steps to my approximate simulation perturbation gadget rounds. So maybe I could use perfect stabilizer tensors corresponding to stabilizer AME states. But like I said, we really require these random tensors to have the proof techniques to show the correct entanglement, which is something that's really important to like keep in our models. So the nice solution, which is to use random stabilizer tensors. So these are tensors that correspond to random stabilizer states. And you can think about these states as I start with some reference stabilizer state, and then I apply a random Clifford unit tree. There's some work to do here because we're now two designs rather than random. You need to check we're not losing anything. And yeah, we checked we weren't losing anything. We proved, firstly, that with high probability, these random stabilized tensors are exactly perfect as we increase the bond dimension. And also going to a two design doesn't mean that we can use the same similar proof techniques to show that we get the good entanglement structure again. And what's really important here to sort of keep a close bound again on the bond dimension and the errors here, because that's what we're using in our whole analysis of like whether this is a reasonable model at the end. Okay, so hopefully that gave an overview of sort of what goes into building up these constructions. So I don't know what the time is. Okay, yeah, so just to summarize our model, we use random stabilizer tensors on QDITs. We use a 2D or a 3D bulk tessellated by particular Coxeter polytopes that we check have all the good properties we want. And this allows us to compose our holographic quantum error correcting code with approximate simulation techniques to provably show that we have the error correcting properties expected in ADS-CFT. We map a local bulk Hamiltonian to local boundary Hamiltonians, and we also exhibit the correct entanglement structure for these disconnected boundary regions. So we give the first model to simultaneously achieve all of these features together. So that's sort of the bulk of the work that has been done. But I think I've got a bit of time to talk about maybe some ongoing work. Does anyone have any questions about what I've said so far? Do you have some like sense of what level of control you have over what kind of properties you can expect from boundary Hamiltonians? For example, I think you haven't specified what you use as an input Hamiltonian. Okay. Yeah, no, that's a nice. If you want it to be frustrated and you want to have like a gap that goes this one over it. Okay, so yeah, I guess this is a nice point. In the real correspondence, there's like one theory, right? There's the theory of quantum gravity and the Einstein equations that describe that theory. And then that is, in particular, is dual to conformal field theories as a group. So while we've recovered some of these features, that's not what we've done here. We've produced a general mapping. I could take any Hamiltonian in the bulk. It doesn't need to at all look like semi-classical gravity. It could be literally anything. And if I use my mapping on that Hamiltonian, I'm still getting the same features that I'm still going to get those three features. So none of those features are dependent on choosing the correct Hamiltonian. And I guess this is sort of like a weakness of the model, but it's also a motivation for developing these models, because one of the questions that we're interested in is sort of at what stage do we need to start incorporating gravity in order to actually get some of the features of ADS-CFT. Like they obviously believe it's inherently gravitational. That's not what we're seeing here. We're seeing that we can get these three features without using any sort of gravitational Hamiltonian. But maybe like as we get closer to like being more like the true correspondence, we're going to have to start putting a Hamiltonian in the bulk that describes gravity, and then we'll end up with a given boundary Hamiltonian that's going to have like particular properties that we want. But at this case, we are just going to get like, we can kind of put anything in and we'll get its corresponding map out. So like there are some Hamiltonians where we'll get a frustrated one, but like I could put in something else, like I put in the identity Hamiltonian, I'm going to get the identity back out. Like,
and what do your interaction strengths look like? Do they actually blow up, or are they constant still?
So they're not constant, but they do become large. And yeah, that's something I feel like I'm probably not going to have loads of time to go through the rest. But yeah, that's something that we're like looking at now in terms of they don't blow up. They're not constant with like the radius, for example.
So you're more concerned about the incidence on the boundary than the interaction.
Oh no, so like where we got the good blow up of ancillars, we also get like a good blow up of the interaction strengths, in that it's like not exponential, it's like polylog in the original one, something like that. I can't quite exactly remember, but it's like controlled in some way. I just didn't quote it. Yeah. Okay. Well, in the last time, I'm gonna. Okay. Well, maybe I'll just quickly whip through like something that we're now trying to do with these codes. So it's all well and good to say we have this code. It kind of looks like ADS-CFT in these three particular ways. It's helping us learn about ADS-CFT if you're interested in that. But something that would be nice to do is actually use these models to try and model something that they're interested in ADS-CFT, but like can't compute for some reason, and kind of see if we can gain an intuition from our models if we have the ingredients to sort of like do a toy version of that in our model. So this is exactly a good candidate for this is position-based cryptography. So like I said before, this uses a prover's position in space-time as its credential. So if I've got an honest protocol, I've got my 4 blue verifiers, and I've got my prover sitting nicely here. Then I've got my 4 verifiers are sending things in, my prover's doing some local unitary, and then sending them out. And if they can do the computation with high probability and they get the right answer, then my verifiers are going to be satisfied that that prover is really sitting there. But say instead I want to do some attack on this. So I want to spoof these 4 verifiers that I'm in this position here. Then I can send 4 of my friends to these positions. And as long as I have some shared entanglement here, then I'll be able to spoof my verifier. And this is so a non-local attack. And yeah, the question, as with all cryptography, is like, how hard is this to do? How much entanglement do I need in order to spoof this? If I need like an exponential amount of entanglement, maybe we'd be satisfied that that's like unrealistic, and therefore this is a valid cryptography protocol. If I could do it with linear amounts of entanglement, then that wouldn't be too reassuring. And what's nice about this area is that the known bounds on the security of position-based cryptography are very broad. So we know that if I have like a simple procedure, then I can do it with linear. So my lower bound is linear in n, and here n is like the size of my input system. So you could think about it as the size of like space that my unitary is acting on. But the upper bound is exponential in n. So we're fully sitting in this gray region where it could be like a really useful protocol, or it could be really boring. And we're not really sure. So what's nice is there's been this proposed attack from holography. So you can kind of see this quite intuitively, that my bulk can do a scattering experiment where I've got some local prover sitting in this region. However, anything that's happening in the bulk is going to happen in the boundary, but I don't have this local position in the boundary. And what's more, I don't have an overlap of these light cones. So there's no place on the boundary where I can bring the inputs from C1 and C0 in and send the outputs to R1 and R0, obeying like the speed of light. That region just doesn't exist in the boundary because of geometry. So instead, I'm going to have to do some non-local procedure. And what's interesting is that it's thought that the entanglement that you share on the boundary in order to implement this is only linear in N. So if we could show this attack in our toy models successfully, and the entanglement needed was only order N, then this would be giving us for free this attack on position-based cryptography, which would basically collapse those bounds and say, okay, position-based cryptography isn't secure, don't use it for things. Right. But like I said, we don't have, this is what people believe happens in ADS-CFT, but there's no like mathematical description of that. So it's not super useful. And we don't live in anti-de Sitter space. So we really want to be able to like put this onto some concrete thing and look at it. And I don't want to go way over time. But basically, like I say, there's essential that there's no overlapping region in the boundary. So great, there's no overlapping. Therefore, I must have a non-local procedure on the boundary. And the question is our model with a local boundary Hamiltonian enough to sort of reproduce this causal structure? So obviously, like I said, localization is essential for causality, but it's not like if I have a causal Hamiltonian, it doesn't necessarily mean I have the right causal structure. And the answer is no, unfortunately. So because I've got these higher interaction strengths, my Lorentzian velocity on the boundary is too high. So I do have like nice light cones, they're just too fast. So I have this whole region in my boundary where this local unitary is causally possible. That's not really what I want. And basically, I might skip over, but basically the idea is we're working to reduce the interaction strength such that we end up back with these like physical light cones that are going at the speed of light and are consistent with the bulk causality. And if we were able to do this, we could then look at how much entanglement we need and actually sort of like implement this position-based protocol in our toy models and see if it works or if it breaks down in some way. And we've made some progress about that, which I wanted to share, but I feel like I've gone on too long. So let me just wrap up. And if you're interested, please talk to me about it afterwards. Yeah, so basically I've given our model of ADS-CFT and maybe pointed out how we're kind of close to implementing this non-local attack, but maybe there's still a few things to work out. But it'll be interesting to work on this more and see if we can like really understand whether position-based cryptography is secure. And then also other work in progress is more generally this crossover of quantum error correction and Hamiltonian simulation. So it's a nice tool of thinking like, okay, my error correcting codes are like perfect simulations. I know I concatenate simulations, so it's sort of like concatenating codes, but maybe I should be thinking about what other techniques are there from maybe Hamiltonian simulation, maybe other approximate error correcting codes that I could kind of put in there to maybe make some gains in terms of locality of my stabilizers or locality of my measurements. Yeah, and they're generally things that I'm continuing working on in that region and we'll be happy to chat to anyone about later. But yeah, thank you.
All right, thanks, Harriet, for the interesting talk. Any questions to, well, I saw Andrew first. Let's go.
Thanks very much. Wondering if you could say something more about the size of the system. Various notions of approximate error.
Okay.
Is it like, yeah, if I make a very large system, if I somehow expect it close to
yeah, so more generally, I'm not sure what the relationship between the size of the system is, but in our particular case of these tensor network models, the error in the system is something that depends on it does depend on n. It depends on the number of tensors in my network. But there are other things as well in there that I can play with. So maybe in order for my error to be constant with n, I can tune something else to scale with n that's not the error. So I would have to look at the exact form of it. But I know it's like there's an interplay of things here to trade off. And yeah, I'm interested, like me and Nudine are chatting more about how we could maybe think about using these sorts of approximate techniques, and if the thing we want to constrain is n, what is the price we pay, and is that interesting?
Yeah, Tom.
So you can relax the tensor requirements of binary, so the choice of the otherwise binary. What happens in the context of Hamiltonian, like choose a non-perfect?
Yeah, so we do our full construction with random stabilized tensors. So we include like this randomness, and that's what's really important to make sure we have the entanglement structure that's expected. So yeah, we don't have to stick to perfect tensors when we're applying these approximate Hamiltonian simulation techniques. But you just need to be careful. Like depending on your choice of tensor, it like feeds into what your boundary Hamiltonian looks like, and then the error analysis of going to a local Hamiltonian.
Matt?
I'm wondering if you can also go reverse from the boundary. Well, they gave you some local Hamiltonian to find on the boundary. Back up the ball.
Yeah, so that way is like the other direction, I guess, is like less intuitive to look at, like from the tensor network picture. But because you don't really want just like your full bulk Hamiltonian to be living in like a small shell, one tensor layer in. So there's like different freedoms that you can choose. And in general, that's the direction that we've thought of. But I think going in the other direction is easier.
Yeah, so Gavin had a question.
So one other part of the AES-50 area is this bulk gauging of global on-site boundary centers. I was wondering if you see any evidence of that in your mapping.
I have not looked.
Or like, maybe about like the global difference between your boundaries.
Yeah, I think in general we should be looking. So we know we don't know how to get like, for example, conformal symmetry on the boundary. But maybe we should be looking into more like symmetries like that we could actually, yeah. I think looking into how symmetries are preserved through these mappings would be an interesting thing to follow up with. But I unfortunately haven't thought about that much yet. But yeah, it'd be interesting to chat.
More questions? Well, let's go with Arkin first.
Right, so when you have this kind of this position-based like a signal and then you have a section on the computational power of the people who like receive the signal, because like if the idea is if they have unlimited computational power, maybe like if you, how should I put this? You can verify if the thing in the middle implemented the right entirety. And the space of data is quite large. Right?
Yeah.
And so you might be able to like learn an exponential number of quantity of information, which you can't do like for the number of.
Okay. Yeah, so in general, I guess we're thinking about these two different sides, right? The verifiers are on their own side. So they've set the task. If they set the task such that they are being really specific for a particular unitary, then maybe they'll allow themselves like a long computation time afterwards. But what's important in the space-time picture is that they're receiving the input at that point, not like later in time. So yeah, there are like different like explicit protocols, some that restrict like unitary to like Cliffords, for example, And then like it's easy to verify. So like there's a whole like family of different things people do. We're mainly just looking at like the causal structure of this unitary exists and can the signals like come in and out. But I think there's like a whole family of different protocols.
Like in that following the unitary, that would be difficult.
No, so in general, we'd want our bounds to be like, so I guess that we'd want the bounds to be for a general unit, for a general protocol. So it's like, okay, you give me some, I know you're doing some protocol, can I attack that protocol? We're sort of working on the side of the attackers, and rather than trying to like make it more secure.
Okay, well, one last quick question.
So you mentioned that you're currently trying to work out how to keep the interaction strengths at a constant.
Mm-hmm.
And I was wondering, for that, are you trying to come up with new perturbation gadgets, or is there some alternative approach to that? Or
No, we're actually trying to think more along the lines of like what I was saying before about the Hamiltonian and the bulk. So we end up with these high interaction strengths, and that's for like a general Hamiltonian. But we think that if we actually look closer at ADS-CFT, there should be some like constraints on this Hamiltonian, and we can use those constraints to maybe restrict our map to only being valid for those particular Hamiltonians, but then also having these lower interaction strengths. So as long as our Hamiltonian could do the scattering procedure, it doesn't need to be like any general local Hamiltonian. So basically, yeah, we're using the bulk Hamiltonian to restrict our map to just working on the relevant Hamiltonians. And in that case, we're able to reduce the interaction strength.
so you're saying that the flow of interaction strength is not a necessary feature of using perturbation gadgets in the first place?
Yeah, so like if we change our initial Hamiltonian, then we'll end up with, like, for example, if I just exponentially suppress the normal of my Hamiltonian in the bulk, then I've trivially exponentially suppressed my interaction strengths. So I've just scaled everything, but that's not what I want to do. But like maybe I can do something more clever than that.
Okay, well, really quick.
Is there a valid question permanent sharpeners proposal as well position is where they say that they prove that if you have large many entangled pairs available, then secure positioning is not possible. But if you're restricting the number of entangled pairs, the amount of entanglement that the adversaries share, then you can make this secure. So it's secure attack value in the second case. Like they provide a lower bound on how much entanglement is needed to make.
Yeah, so when I gave the gray region, that's for like general unitaries. So there are some cases like, for example, if I know my unitary is Clifford, then I know I can break that with like less entanglement than exponential. But that doesn't ruin position base, because then you just say, okay, I won't use Clifford's then. But so there are like more bounds. If we were able to show our protocol for general unitaries, we would be tightening this bound, because we'd be the lowest bound on entanglement for general unitaries is linear.